Okay, so the video got ended somehow. Okay, so what we were discussing the UDL, which is acting on this beam. UDL is uniformly distributed load, which means that the same magnitude of load is being acted along the entire span of the beam, or that the loading is constant along the span of the beam. We are denoting the magnitude of UDL as W, which should have a unit of kilonewton per meter or newton per meter or newton per millimeter. Okay, so this denotes this loading. This UDL is a magnitude which is applied per meter length of the beam. Okay, so in order to find the magnitude of W, we have to first calculate the maximum bending moment due to this loading. So how are we going to calculate the maximum bending moment? From this expression. Okay, now we can easily ignore this expression because these values are not provided in the problem. Okay, what do we have? We have this value sigma. We will be able to calculate I, which is the moment of inertia, and also we will have we can calculate the value of y. Okay, so we can rearrange this expression as sigma is equal to m by I into y, or I'm so sorry, we can write it like this because we have to calculate m is unknown here. It is going to be sigma by y into I. Clear? Now let us calculate first I is equal to BD cube by 12 for a rectangular section. See, the beam is having a rectangular cross section, and the moment of inertia for this rectangular section is going to be BD cube by 12, where B is 150 into 250 cube divided by 12. Okay, what is Y? Now I have another thing to say, that is F permissible or sigma permissible or permissible stress is provided. So the beam is going to experience permissible stress at the topmost fiber or at the bottommost fiber. So at the topmost fiber, what will be my value of y be? My value of y will be equal to 250, the total depth of the beam, divided by 2, which is 125 mm. We have already the value of sigma permissible. Okay, so we will simply substitute the values of sigma permissible, that is 10, divided by y is 125, into I is calculated as 150 into 250 cube divided by 12. Okay, so I will ask you to calculate this with the help of a calculator. I am writing it down straight from the material from where I'm showing this problem. The answer is given as 15625,000 Newton millimeter. Okay, Newton millimeter. So from this value of maximum bending moment, we can easily calculate the maximum loading. Okay, so now since the loading is equal at the entire length of the beam, it is a symmetric loading. Okay, and since it is a symmetric loading, the bending moment is going to be maximum at the center of the beam. Okay, in every beam with any form of loading, there is a point where the bending moment is going to be maximum, and for this beam which has a UDL acting upon it, the bending moment is going to be at the center because of the symmetric loading. Okay, so as we have discussed in the previous classes or in the earlier classes about how to calculate the bending moment or the maximum bending moment for UDL, we have already seen that the maximum bending moment for UDL throughout the beam is equal to WL square by 8. Okay, so now what we have to do, we have to simply substitute the value of this m max in this equation, and we know L, which is 5 meter, and 8 is a number, so we write m max as 15625,000 is equal to W into L. See here, we have taken this value as Newton millimeter, so for L also we will take the value of in millimeters, that is 5000 square divided by 8. So if you calculate the value of W, it is coming as 5000 Newton per meter or 5 kilonewton per meter. Okay, so this is my value of the UDL, or the magnitude of the UDL which is being acted on this beam.